Welcome to the new topic of solar electric panel design and calculation. For that, we must have the following skill set: basic knowledge of AutoCAD 2D, emergency power demand calculation on Excel sheet. Participant will be able to implement emergency power demand calculation, solar panel sizing, secondary power supply calculation. By this project, we will learn solar panel sizing, emergency power requirement for the building, battery backup and the battery sizing, and switch over to alternate power supply. The target student for this topic is electrical engineers who need to calculate the solar electric panel system. Then electrical draftsmen who need to design the solar electric panel. Then MEP engineers, mechanical, electrical and plumbing engineers who must have the knowledge how to design the solar electric panel system. And the student who wish to learn the solar panel designing. By the end of this project, you will have the following skill sets: solar panel sizing as per power in kilowatts, solar power collecting in UPS or the inverter, power saving or the electric bills reducing by power units, eco-friendly and environmental friendly system design. This project contains solar panel sizing, then alternate power demand calculation and solar panel mechanism, and 2D or SLD diagram for solar electric panel, and the last one is wiring diagram for solar panel to UPS or the inverter and the electrical equipment, that is passage street, staircase lighting, lift power and water pumps, etc. By this case study, for example, provides uninterrupted power supply to the building services in case of power failure, that is passage, staircase and street lighting, as well as the lift. Power saving and economically useful. Solar electric system is the power saving as well as the economical useful. It is also useful as the alternate or secondary power supply for small bungalow or small scale building. Following scenarios will be covered as a part of this case study. Solar panel single line diagram, that is called SLD. Emergency power requirement. Power requirement calculation in kilowatts. Wiring connections from panel to UPS or batteries. Welcome to the tutorial of solar electric panel system design. In this topic, we will learn that how to design the solar electric panel. Solar electric panel, also known as solar PV models, that is solar photovoltaic panel. Solar electric panel are generally using to save the power, and in case of power failure means in case of power emergency. So that to design the solar electric panel or PV panel system, we need to calculate the actual or emergency power demand required for the building. So that to calculate the power demand, we need to operate the Excel sheet. To calculate the actual power or the actual power demand, we need to calculate into the Excel sheet like this. There is the serial number, the area of application or the appliances, power in watts, the power required for that appliances into watts, and the quantity, and the last one is the power in kilowatt. So this is how to prepare the Excel sheet to calculate the electrical power demand. For the serial number 1, we need to calculate the power required for the typical flat for the building. Suppose in case there is a one building and into that building there is the multiple typical flat is available. So we need to calculate each and every flat power demand. So for example, I will calculate typical flat power demand required. So I will mention over here into that the serial number 1 is the LED or CFL bulb. For the LED or CFL bulb, the actual power required is the 40 watts. Suppose in one typical flat there is the 8 numbers of CFL bulb, so the total power is power in watts multiply by quantity divided by 1000, means 1 kilowatt is equal to 1000 watts. That's why I need to multiply it divided by 1000. So it is the answer come in a 0.32 kilowatts. Same, the appliance number 2 is the fans. If in a typical flat there is the 3 number fan we need to run, the power required for a typical fan is the 80 watts. So the total is 0.24 kilowatt. Same, if we need to run the TV into our typical flat, the power required for the TV is around 120 watts and the quantity is around 1. So the total power required for the TV is 0.12 kilowatt. Any supply, for example 6 by 16 ampere connection we required, the power generated by the 6 by 16 ampere is around 3000 watts. Quantity 1 number, so it will around 3 kilowatt. So the total power for one flat is around 3.68. This is the total power required in flat in case of emergency. Now we need to calculate the common area like lift, passage, corridors, etc. For that, I will calculate first for the common area. I will calculate the passage lighting requires one bulb required 40 watts, and around, if in the passage the entire building has the 100 bulbs, so the power required for that 100 bulbs is approximately 4 kilowatt. Then I need to calculate the street light. Or the compound light. For example, each street light bulb gives the 100 watts. The total quantity is around 20 numbers, so it will be automatically come 2 kilowatts required for the street light. Staircase lighting. Suppose the staircase lighting, each bulb has the 60 watts and the number of staircase lighting is around 20. So the total power required for that staircase lighting is around 1.2 kilowatt. And the emergency service like lift. Lift also required the emergency services, emergency power. So it is around, each lift takes the 400 watts. So around, if there is a 2 lifts, the total power required for the lift is around 0.8 kilowatt. Water pumps. Next is the water pumps. Takes around 3000 watts for each water pumps. If there is a 2 water pumps for the building, it will take 6 kilowatts. So I need to calculate the total power demand for building is around, we need to calculate the total power required for the building is around typical flat plus the common services, that is 17.68. So with the buffer for the average, we need 18 kilowatt power for the entire building. So this can I calculate the entire power demand required for the building. So I need to generate the 18 kilowatt from the solar electric panel. By calculating this 18 kilowatt, I'll design the solar electric panel into the AutoCAD drawing accordingly. So for 18 kilowatt, I will design the solar electric panel. To design the solar electric panel, we required the multiple components. Solar PV system includes different components that should be able to select it accordingly to your system types, site location and the application. The major components for the solar PV system or the solar electric panel are the below. The important components required for the solar electric panel is PV modules, or it is also called solar photovoltaic modules. Solar photovoltaic panels. Solar photovoltaic panel made out of cells which takes the sunlight and convert that sunlight into the electric power. So the PV modules is a very important part of the solar panel system. Solar PV modules convert sunlight into DC electricity and current coming from PV panels. The next important part for the solar electric panel is solar charge controller. Solar charge controller regulates the voltage and current coming from PV panels going to the battery and prevents the battery overcharging and prolongs the battery life. That's why we require the solar charge controller. The third main important part in a solar electric panel is the inverter. Inverter converts DC output of PV panels or wind turbine into a clean AC current for the alternate current appliances or fade back into a grid line. It means the inverter is the important part which converts your DC output into the AC outputs. That's why inverter is a very important part. The next part is the battery. Battery stores the energy from supplying to electrical appliances where there is a demand. It means when there is a demand by the appliances or by the any flat, the battery gives the power to that particular appliances. So the battery is important, and the design of battery bank is also important in case of solar electric panel design. So these are the four main important parts required for the solar electric system design. Now by this we need to calculate we need to determine the power consumption for the entire building. The first step of designing a solar PV system is to find out the total power energy consumption of all loads that need to be supplied by the solar PV system, so that I have calculated this power demand into the Excel sheet. The total demand for the entire building is 18 kilowatts. So I need to design the solar electrical panel which provides the 18 kilowatt energy to the entire building. For that, I need to design the solar electric panel. For example, the solar electric panel has the standard size of the solar electric panel is 77 inch to 39 inch. 77 inch is the length, whereas 39 is the width of solar electric panel. 77 is approximately 2 meter and 39 inch is approximately 1 meter. So I will design the solar electric panel into the metric system, that is 2 meter length and 1 meter width. So this is a typical solar power panel. This solar power panel provides this solar power panel provides the electricity of around 450 watts. It means one power panel provides the 450 watts. So if my entire kilowatt is 18, my entire power requirement is 18 kilowatt, what I required is the 18,000 divided by 450. So 40 arrays what I required to the entire building. It means 18 kilowatt into 1000, that is the 18,000 watts. So this 18,000 watts total energy required, or the total electricity required for the entire building. So what I required is the total 40 panels on each grid, so that the 18,000 is there and divided by 450. So I required 40 panels to create the entire 18 kilowatt energy. So this is what I am doing. I need to assemble like this. This is entire 4 panel is there, and I need to draw the 10 column and 4 rows, so it will become the 40 panels. So these are the 40 panels for the entire building, so that from here to here there is the total length of the building must be more than 20 meter, so that the panel can be arranged accordingly. So this 450 watts each panel multiply by 40 creates the 18,000 watts, that is 18 kilowatts. So this entire system gives the 18 kilowatts power. It can be divided into 2 part, 3 part accordingly as per our requirement, so that it can be there must be the space between these two, or it can be arranged typically so that it can be space saving. So from there I will design the power generation cable from here to the inverter. So there is the inverter, or in between the inverter to the PV modules. This is the PV modules. I have arranged this PV module as per requirement. From the PV modules here, so from the PV modules the cables goes to the solar charge controller. So I will draw here the solar charge controller cable. One is the supply and one is the return. So the cables is like this. The controller cable required for the solar electric panel. So here is the solar charge controller this is the solar charge controller. The solar charge controller takes the command. The solar charge controller regulates the voltage and current coming from the PV panels going to the battery and prevents the battery overcharging and prolongs the battery life. So that command is each power saving into the inverter must be come from the solar charge controller. From the solar charge controller, there is the cable like this. As we calculated the 18 kilowatt, the solar charge controller capacity is around 18 kilowatts and the standard is 230 volts. This is solar charge controller. The capacity of solar charge controller is 18 kilowatts, 230 standard volts is there. From there, the cable is going to the inverter. So this is the inverter. The capacity of the inverter is totally depend upon the battery size. Battery capacity is calculating in a ampere per hour. For example, 10,000 ampere hour, 2000 ampere hour, 3000 ampere hour, multiple ampere hour is applicable. Select the battery cell capacity accordingly to your backup needs. For example, I required the battery backup for 18 kilowatts. So my battery size will be 18 kilowatts accordingly. Now how to size the inverter? This is the inverter required for solar electric panel. Inverter sizing is very important part. An inverter is used in the system where AC power output is needed. The input rating of the inverter should never be lower than the total watts of appliances. The inverter must have the same nominal voltage as the battery. For standalone system, the inverter must be large enough to handle the total amount of watts we need using at the one time. The inverter size should be 25 to 30% bigger than the total watts of the appliances. It means our requirement is 18 kilowatts, so the inverter size may be 30% more. For example, it must be around 24 watts, 24 kilowatts. For example, if my kilowatts is around 18 kilowatts, if I required the 30% more, so 18 multiplied by 1.3, it is around 24 kilowatts. So my inverter size is around 24 kilowatts. So that I will calculate the inverter size 30% more than the required power. In case of appliances type is motor or compressor, then the inverter size should be minimum 3 times the capacity of those appliances. Because in a motor there is the torque load, and at the starting point the torque loads take the double or triple power of the normal power. That's why the inverter size at the time of selecting the motor and the other size, we required triple time capacity of the normal type. So this is how to design the inverter sizing. For example, if my entire load is around 18 kilowatt, so my inverter will be 30% more, that is 24 kilowatt. Now the inverter requires the battery. So the inverter requires the battery. Battery cells are connected into the series like this. This is the battery required to save the power. Battery bank is something like this. There is the multiple rack available into the battery bank. So into the multiple rack we can save the battery accordingly. So this is the battery bank. Inverter saves the power into the battery bank, and then we can use the battery as per our requirement. Battery capacity calculating as per the total demand required for per day. How to size the battery bank or how to size the battery? The battery type recommended for using in solar PV system is deep cycle battery. Deep cycle battery is specially designed for to do the discharge to low energy level to the high energy level. The battery should be large enough to store sufficient energy to operate the appliances at the night or cloudy day. To find out the battery size, we need to calculate the battery size as follows. To calculate the battery size, there is the formula. For example, battery size is equal to battery size or the battery capacity in ampere hour total watt required per day by the appliances multiply nominal battery voltage So to calculate the battery capacity, we need to calculate the battery capacity in AH, ampere per hour. Standard formula for the battery capacity is equal to total power in kilowatt divided by standard volt. So if the total power is around 18 kilowatt, standard volts 230 volts. So according to this, the standard ampere required is around 78 ampere per hour. So this is the battery capacity we need to calculate as per this formula. And the multiple banks as per the requirement. For example, we required total 8 hours or the 12 hours. So accordingly, the battery will be 12, 8, like that. So here I will design the total number 8 battery will be there, which gives the power to the entire appliances. So this is the battery bank's battery capacity, total power in kilowatt divided by standard volts. So standard volts is around 230 volts and the entire power required or the power demand is 18 kilowatt. So battery capacity is 78 ampere. So for example, if we required the battery must be run for the entire day, that is 12 hours. For 12 hours, our battery capacity must be 12 into 78, that is around 1000 ampere. So we required battery capacity around 1000 ampere hour. This is the battery calculation, and the next is the appliances from the inverter. For example, the appliances is going from here to each inverter. Suppose the typical flat, the entire system is designed like this, typical flat and the common area. So the from the battery goes accordingly. For example, this is for typical flat. This is for passage lighting. The next is street light. Staircase lighting. Staircase lighting. The next is lift that is passenger lift. So the passenger lifts